Following similar workflow, we elucidated another structure which is a little bit more complicated. As before, this compound has exchangeable proton. And both carbon NMR and the PT135 spectra give us good information about the number of carbons and the type of the carbons in the molecule. From HSQC spectrum, we have, again, very good one-bond CH correlation, and we can identify connections of carbons and protons from this spectrum. When we tabulate the data, we can notice that the number of carbons and protons is different than what the molecular structure tells us. And it's exactly twice lower. So the hypothesis is that it could be a dimer of a certain kind, which is often happened during different chemical transformations. So for this impurity, we also collect COSY 2D NMR. And when we analyze the spectrum, we can identify that the proton 8, for instance, correlate with the proton 5, and also to the proton 6. Proton 6 and 7, they both correlate to proton 5, and so on. And again, I would mention that the signals on the diagonal, they're basically useless because they represent themselves. So when we finish analysis and plot the data, we can see that there are certain correlations, there are a number of correlations of proton number 2 to 4, 3 to 4, 5 to 6, 7, 8, 6 to 5, 7, and 8. And exchangeable proton doesn't have any correlations in this case, which is not untypical. So here the spin systems look like this. Again, because we know the chemical route from where the chemistry appeared, we also can use our information that the structure is aromatic to create this system. So the spin systems 3, 4, and 2 gives us this type of fragment structure, which is a part of aromatic ring. 6, 7, 5, and 8 have very strong correlations, and they're connected as an allyl group. Proton 1, spin system 1, is most likely the fragment connected to the nitrogen atom. An exchangeable proton is connected to the hydroxy group in this case. And again, because correlation ends with the CH, CH2, or CH3, we can just add quaternary carbons where the correlation ended in the fragments to expand our fragments a little bit. Moving forward, we want to analyze long-range correlations and determine how we can connect those structures, how we can make, our picture more complete. So from HMBC spectrum, we put all correlation in the last column of the table, from where we can see, what carbon correlates to what proton. In this case, a little bit more complicated, but it's still very well resolved. We can see that spin system 1 is connected to quaternary carbons CC and CB. So we just add them to this fragment. And because it's an aromatic structure, and we have 3 quaternary carbons, 3 aromatic quaternary carbons, and 1 was missing, we just add this here. Because aromatic ring should have 6 carbons. Spin system 2 is connected to carbon CB. And actually, it's exactly the same carbon as here. Spin system 3 is connected to the quaternary carbon CC from this correlation. And again, this carbon is also there. An exchangeable proton is connected to the quaternary atom A. and the quaternary atom is here. So now we have very extensive information about connections of all these fragments, and we can move forward, connecting them, closing the aromatic ring. And finally, drawing the structure, which is exactly the dimer of two aromatic fragments. The final structure should look like this at the end. This compound was also isolated and completely identified just by means of NMR. We haven't used X-ray data here or any of the more complicated and expensive NMR techniques.